much to the organizers. It's a wonderful workshop. Okami-san just gave an overview talk on neuromorphic computing, and I would like to deepen our discussion of one specific field, spiky neural networks, because they are very special, they're very biologically plausible, perhaps the most biologically plausible type of neuromorphic computation. They closely adhere in the biological principles of the human brain. And therefore, if you ever hope to build machines which truly think like us, we should focus on spiky neural networks. And yet, if you read the news, you'll hardly ever read about this type of neural networks. And the short answer of why is that we don't have the right hardware to run them properly. So today, I will talk about what exactly this hardware problem is and where it hides, what we can do with that, what we have recently done to advance in the solution of this problem. We made this very simple and yet very biologically plausible devices that are uniform as well. And most interestingly for you, perhaps, I'll talk about what you can do following these principles in your material system. What simple questions you can ask about your material system to determine whether it may be interesting for neuromorphic computing and for spiky neural networks. So first, let me just show you simple numbers proving that CMOS is struggling with spiky neural networks. This is a work from 2008. They simulated a tiny fraction of the human brain at a slow speed, and it requires 60 CPUs. So if you just extrapolate that linearly to the size and speed of the human brain, we'll get an equivalent of 36 million CPUs, which is just hopeless. There's another approach. Instead of using non-Newman architectures, we can use CMOS components to construct synapses and neurons. And this is what it would look like. And if we assume that we need just 10 transistors per synapse and 10 per neurons for simplicity, we'll get this number of equivalent CPUs, which is better than 36, but still pretty hopeless, right? There are some composite approaches in which people use some features of neuromorphic architectures and some features of conventional von Neumann architectures, like in this works from IBM and Intel. And it gives some good results. The problem is we are still very, very far from the goal, from the human brain. There are 4 prominent works from the last decade, 2008 to 2018, and in all of them, what we have is roughly 1 million of neurons, on the order of that. So there's been no scaling in the last decade, and if you compare it to the Moore's law, which some people say is about to break, it's actually doing much better with black dots than scaling of spiky neural networks, which are red and dark red dots. So we have 2 groups here. These are like exploratory spiky neural networks. People use them to prove some concept or to demonstrate something. And they have roughly 1,000 neurons, which is a tiny amount. And this is like high performance spiky neural networks. People deliberately increase the number of neurons as much as possible. They use huge clusters for computation. They use deliberately developed hardware, like in these cases. But still, what we can get now is just 1 million of neurons, not more than 10. So if you extrapolate this trend and compare it with the goal, we'll understand that we'll probably never get here to the size of the human brain if we keep sticking with CMOS. And even a pigeon's brain is far too ambitious for us right now. So a question that you might have is, do we really need this huge number of neurons in the system? Or maybe we can get away with something much smaller and simpler. And unfortunately, the answer is that we do. This is a research from neurobiologists, which show that logarithmic brain mass is linearly proportional to global cognition. Or in simple terms, if you want to get smarter, go get more neurons, and there is no other way around this. So we must have super large neural networks, and CMOS cannot provide that. So we need new technologies, new materials, new physical concepts. First, let's look at what we require from these concepts. You've seen some parts of this picture multiple times already. I'll still brush up because it's important for understanding. So we have a couple of biological neurons here, and what neurons do is they integrate incoming pulses, incoming spikes from other neurons. And if this integration exceeds the threshold, a neuron will fire its own spike, propagating down the network to all other connected neurons. Very importantly, this integration is leaky. So if the sequence of spikes is sparse enough or not long enough, your neuron will not fire, and basically nothing will happen. You can increase the probability. This is probability, basically, sweeping from 0 to 1. You can increase that probability by increasing the number of pulses or packing them denser in a sequence. all neurons are connected via synapses, which are like attenuators or resistors. What's special about them is that their resistance is not constant, and it changes based on the arriving times of pulses from the pre-neuron and from the post-neuron that are connected by this synapse. And this is what the function looks like. It's called spike time independent plasticity. You have the first neuron fires first, and then the second one, synapse increases its weight, making the connection more transparent for all consecutive pulses. However, if the second neuron fires first before the first one, the synapse kind of thinks that the causality relation is broken here because it expects everything to propagate in this direction from left to right, and it makes a connection less transparent for all consecutive pulses, and that's why we have the second negative branch. And the tighter the pulses are correlated in time, the bigger is the weight update. So if pulses arrive in completely different times, nothing changes in the synapse. So we need these two functions, leak, integrate, and fire, and STDP in our novel material systems. Have there been any examples of such works? We all know that the answer is yes, actually, many examples. Fukami-san mentioned some, Professor Ingrid mentioned some. So I'll show you some as well, because it is important to understand how it all works. All synapses to this date work on the very same technology that is applied in the human brain. We have bipolar nonlinear pulses like this one, and these pulses propagate in your network. What's important is that they are sub-threshold. So if just one pulse arrives to a synapse, nothing happens. If two pulses arrive closely enough in time, they will sum their voltages, and there will be a burst of voltage over the threshold, which will make a change in your synapse. Depending on the causality between these two pulses, first comes first, second comes second, or vice versa, the burst will be of different voltages, and therefore the update will go in opposite directions. If you look at it, we'll figure that all we need to realize is in an artificial system is a thresholded memristor. So you have a memristive device, and you have a dead zone in the middle, so if a small pulse arrives, nothing happens. But if there is a burst, you'll see a change in the state of the synapse depending on the polarity. And if we just combine these two things, we'll get, well, kind of like STDP in our ferroelectric cell. This is work from Julie Grelier's group. So the thing is, all you need with this principle is just a thresholded memristor, and that's why we have so many examples of artificial synapses. Right, now a neuron. This is an example based on the Mott insulator, and this is very elegant because the Mott insulator is usually insulating, but if you apply a sequence of pulses, they will trigger formation of metallic sites in the bulk, and if you apply enough pulses, these metallic sites will form a bridge, and you'll see a spike, which is equivalent to firing of a neuron. And these metallic sites tend to relax over time, so this is how leaking is implemented. So this is very neat. And at this point, you might have a question. What's the problem then? If we have synapses, we have neurons, we just need to combine them into a circuit and see how consciousness emerges. But it's not the case, unfortunately, because the materials are different. And if you think about it, when you need complex 3D circuits with very dense interconnections, it will be almost impossible to combine them into a truly functional system. But even if we imagine for a second that we miraculously did that, they will not understand each other because they use different pulses. All synapses, as I said, uses biological bipolar pulses, but if you apply them to a Mott insulator, nothing will happen because on average, these pulses are 0. If you apply this rectangular, or some people use triangular pulses, unipolar ones, to a synapse, it will just max out the state of the synapse to one of the terminal states, and that will be it, no synaptic functionality. And they don't work together not because I carefully picked the references. You can check all of these references with the most biologically plausible examples. You won't find a pair of compatible synapse and neuron, neither in material system nor in operating principle. And this is not a coincidence. This is a trend, basically. And it's very understandable if you look at the differences between neurons and synapses. Neurons are binary. They're either firing or not firing at any given moment. They're volatile. They are leaking constantly. There's no long-term memory. And they're stochastic. Synapses, on the other hand, are not binary. They're memristive. They're non-volatile. They're basically the memory of the brain. And they're not stochastic. They're deterministic. That's a lot of differences. And now it makes sense why, when you're trying to build a neuron, the more you're trying to build a neuron, the less you are building a synapse. and vice versa. And I haven't even mentioned that the immediate responses have, well, virtually nothing in common, STDP and LIF. You might say then that, well, in conventional architectures, it's not a big deal, right? We have a CPU based on one technology. We have memory, which can be even MRAM, and they work nicely together. But that's because we have an interpreter between these two devices, a memory controller. And we have just one bus, so we need just one memory controller, and it all works. Now let's look at the architecture of a spiky neural network. This is a very simple representation, of course. We have 1 quadrillion of synapses with black squares, green squares. Each synapse is connected to a couple of neurons, so we have 2 quadrillion buses in a system. Or if we look at it from a different perspective, usually people from banks use this kind of charts, but we'll borrow it from them. In a modern laptop, we have something like 7 trillion transistors in a CPU, something like 8 trillion memory cells if it's 1 terabyte of storage. And there is a bus somewhere here. You obviously don't see it because there is just one. Now, if we look at spiky neural networks, we have this share for synapses and this share for buses. And neurons are somewhere there. You just don't see them because there are too few of them. So buses dominate the architecture, and we keep ignoring them. And that's why we don't have the right hardware, because buses outnumber all other devices combined. Now, what can we do about it? There are 2 options. First, we keep insisting that we use uncompatible devices, and we build a converter into every bus. But if we imagine that we need just 1 transistor for a converter, which is already fishy, we'll need an equivalent of 300,000 CPUs only for the buses, which is, again, hopeless. So we're left with just one option. And the option is to demode these buses from the state of separate components of a circuit back to where they belong, basically just simple conducting wires. And in order to do that, you must have compatible synapses and neurons. So that is that hardware challenge, the big problem that I mentioned in the introduction. And now I'm going to show how we managed to resolve it, at least made some initial attempts to do that. So let's simplify functionality of synapses and neurons, because otherwise it's too overwhelming. And we break it into 2 parts: states that the devices can take and rules that govern the evolution between those states. So for a neuron, we have binary, firing, not firing. For synapse, we have multiple states. That's just biological representation. Don't mind it. And as for the rules, we have leaky integrating fire and spike time independent plasticity. So let's forget about the rules for a second and focus on the states. So you need to realize them uniformly. What do you need for that? A material system which can be binary and which can be memoristic at the same time. And we recently found such material systems. So I'll switch the gears and talk about Spintronics for a couple of slides. This is a quite well-known system, antiferromagnet, ferromagnet. We first made it several years back to show that field-free spin-orbit switching is possible in very simple lean stacks. All you need is to replace heavy metal with an antiferromagnet with strong spin-orbit interaction, like platinum manganese in our case. You get spin-orbit torques, and you get symmetry breaking because of exchange bias at the interface. So you get field-free spin-orbit torque switching. This is what we expected. What we didn't expect was that it would be non-binary, memoristic. So you can set different device states by applying different currents, and they will be stored in a non-volatile manner. So we decided to dig deeper into this. We fabricated devices of different sizes. Large devices are memoristic, but smaller devices already show pronounced intermediate steps. And as you get even smaller, you have less steps until you hit binary regime below 200 nanometers. This is a clear indication that, in fact, your switching is analog-like switch is an ensemble of multiple binary switchings of different parts of your system. And this is what we confirmed recently with XMCD in collaboration with Professor Gambaldel's group and Diamond Light Source. There's a separate poster about that by this guy, Gunashil. I do recommend it to check it out because it's a separate, very interesting story. Now the question is what varies between different parts of the sample? Why don't they switch at the same current like decent devices do? And the answer is that exchange bias. So we have different parts of the sample, and they all have different in-plane and out-of-plane components. So exchange bias, we have this distribution for in-plane component. It makes sense that it's shifted because we anneal the device for that to set exchange bias. Surprisingly, out-of-plane component also varies a bit. So there's some tilt of effective exchange bias field up and down. And you will never see it with a macroscopic measurement like VSM. So we devised a couple of techniques to probe this and that. Unfortunately, there's no time to talk about them. What I'll say is that we basically just tick the first box. We have a system which can be memoristic if you make a large enough device, and which can be binary if you make a small one. And what we actually do in this work, we use the very same thin film and just pattern it into devices of different sizes. And this is how we get the dummies for synapses and neurons, because what we've got so far are just dummies, the state. Now we have to make it all work somehow. So how do we do that? Well, the only chance is to find something in common between these two things to realize it uniformly. So what is in common? Let's look at the synapse first. We have these pre and post pulses, like I explained. Let's imagine you are a synapse. So what do? You have a timer. You start the timer when the first pulse arrives, and you stop the timer when the second one does. You don't care, and you don't know about the rest of the circuit. You only care about yourself and your timer. So what you need for your functionality is a measure of local time. OK, so if you can find a measure of local time, some time-based functionality in a Lick integrated fire, this will give us an option. But if you look at the horizontal axis, it's excitation intensity. So it's not quite the time, right? But then if you think about excitation, what's excitation intensity? It's a number of pulses arriving within a certain time period. So here you have the time. If you apply a sparse sequence, as I showed, a neuron won't fire. But what you can do instead of increasing the number of pulses, you can just put them denser together. And it will trigger the neuron because there will be less time for the potential to dissipate in between the pulses. The pulses are the same. The sequence is the same. What differs is just the time. So we need to realize local time for this functionality and local time for this functionality. And this is what we're going to do in the system I described. Problem is, it's a very simple one. This is a whole bar. There is a pattern dot. We have a switch for short pulses for switching, for DC current, and a voltmeter for whole resistance measurements. And that's about it. This is what it looks like, a binary device in SEM. How do you measure time with something like this without any auxiliary circuitry? The only chance that you have is to use some physical process in the system that you can excite, which then will start relaxing, and then you will read it out with another pulse. Something like that. So you excite a timer, you start your physical process, it relaxes in between the pulses, and then it affects switching by the second pulse. So if it arrives here, it will produce a different change as compared to if it arrives here. And for that dynamical process, we need to find some dynamical processes in the system. And the best way to start is just to try to switch it with pulses of different width. So we switched it by second pulses, shorter pulses, nanosecond pulses. It all works, which is, by the way, an indication that field-free switching, memoristic switching, is as fast as conventional switching. We also tried sub-nanosecond pulses, and they do work. But there is no dynamics here that we would see clearly, right? So there's another representation. We have a phase map of switching. This is a memoristic device, so note that this is not probability like in conventional cases. The color is the degree of switching. So we initialize device, apply a certain pulse, and see how much it has switched. And you can see that there's no dependence of switching current down to roughly 10 or 20 microseconds, but then it increases sharply. So what's happening there? There's definitely something going on, right? And we can clarify it with a technique called trains of pulses. We basically apply, I'm not sure if that is visible, we basically apply, this is 10 millisecond pulses, 1 millisecond pulses, 100 microsecond pulses. And they all fall on the same trajectory, and we have integrated time of the sequence at the horizontal axis. And it makes perfect sense because we keep all parameters fixed. We use the same voltage, the integrated time is the same, torques are the same, everything is the same. So it's all good. But then when we hit this 10 microsecond region, it starts to break. This is the blue one, is 10 microsecond. And as we go to shorter pulses, it breaks completely. So what's going on there? Well, keep in mind that all parameters are still the same everywhere here for the same time. So the only option that we have is temperature. The temperature is not saturated. When a pulse arrives, it heats up the sample due to Joule heating and assists itself by destabilizing magnetization. So we tracked how temperature evolves, and this is the dynamics, and you need exactly 10 microseconds for the saturation, which agrees with this perfectly. If you are still not convinced, I'll just show you this graph. We try to measure RI loops by 10 nanosecond pulses at room temperature, this blue line, and then we increase temperature, external temperature due to a heated stage up to 150 degrees Celsius, which is this upper line, and you see that switching increases drastically. So temperature does affect the system, and pulses do generate temperature. So this explains why we have this curvature, and it gives us a chance to build a temperature-based timer. Because you can excite the dynamics by arriving pulse, it starts to relax in between the pulses, and it affects switching by the second pulse. So we tick all three boxes here. Now let's look what it would look like. A couple of pulses like STDP pair, positive, negative, otherwise exactly the same. And this is what temperature dynamics is like. So the first pulse will receive on average this temperature. The second pulse will receive larger temperature due to the residual heat from the first pulse. And we expect the second pulse to produce more switching in the system. So how do we test it? We have a hysteresis as this loop. We initialize the device to the ground state by, say, magnetic field. And then we apply a pulse of positive polarity. So the initialized state is uniform. Can this pulse produce any switching in the system? No, it can't, because it's already initialized, right? But what it will do is that it will heat up the sample. And some heat will go to the second pulse that we apply, which is exactly the same, but now has the opposite amplitude. So it will produce some switching, but the amount of switching will depend on the delay between these two pulses, on this residual heat that the second pulse arrives from the first one. So we decided to choose these two delays, two terminal cases for these delays. One is 50 nanosecond, much, much shorter than the characteristic time scale for the temperature, 10 microsecond. Second is 1 millisecond, much, much longer. So I call this a hot pair because there is a lot of residual heat from the first pulse to the second one. And this is called a cold pair. And before each of these pulses, we initialize the system, of course, by a magnetic field, and now we look at the difference. And there's clearly a massive difference. You cannot see the axis, but it's like more than 20% of the total change of the device resistance. So it's very noticeable. And if you look at the phase diagram I showed you before, you'll see that it goes straight along this border between the non-switched and switched cases, which makes sense, because if you apply to small pulses like here, they are too small to make any change in the system. If you apply to large pulses, second pulse doesn't care about the residual heat from the first pulse. It can switch everything by itself, like here. So there is no difference. It's zero. And at the border, you have the region of maximum efficiency. So we decided to pick a pulse from this red region for STDP functionality. Now, what you need for an STDP functionality, well, it's now very simple. You just take these two pulses with maximum efficiency from the phase diagram, and you vary the delay between them, and this is the function that you get. Color represents the amount of extra heat for the second pulse, and this is the principle. So the system is demagnetized in this case. We have equal number of up and down domains, roughly. This is important, difference from the previous slide. The first pulse arrives, and it produces some switching in the system because it's large enough. And also, it leaves some residual heat for the second pulse, which is exactly the same, but now comes from the opposite direction. So it also produces some switching, but more than the first pulse if the delay is short enough due to the residual heat from the first pulse, right? And this is how we get this STDP function. And this is very biologically plausible. This is an actual STDP function measured in a classical work from 1998. And you can see that everything, every feature is the same. And even in the central region, we have reduction of the change in the biology. And we have reduction here because pulses simply overlap, so they cancel out. Now, real learning in our brain happens during multiple iterations. So we need to apply not just one pair of pulses to a synapse, but multiple pairs of pulses. And this is how it happens in our system. So we choose first a delay with negative sign, negative causality, basically. We start from the Dmax state and apply multiple pulses. And in roughly 200 pulses, synapse has learned its state. So it converges to one whole resistance, one magnetic state. Then we swap the polarity, swap the causality, and it converges again to the opposite state. If we change the delay now, the system will converge to different states. And if you look at 1 millisecond, which is very long, so we have no correlation between the two pulses, practically nothing happens to your synapse, which makes sense, and this is exactly what we want. So it stays around this 0 region. This is a simulation from a neurobiological paper arriving rewards or spikes, and this is how synaptic learning occurs. Now, well, that's pretty good. We've got a synapse. Now we'll try to use the same principle in that binary device to build a neuron. And it's very simple. I don't even need to give any explanations. Basically, you apply one pulse. It's too small to switch magnetization, but it increases the temperature. You apply multiple pulses, and they eventually heat up the sample sufficiently for magnetization reversal to occur, which is equivalent to a firing event of a synapse. So we try to fix the number of pulses and vary frequency, and we also try to fix the frequency and vary the number of pulses. And in both cases, we could sweep the probability from 0 to 1, which is just what a neuron should do. And if you look at the insets waveforms, you'll see that there are no intersection between them, no overlapping. So this functionality is not because we have increased voltage, because the pulse sequence is too dense. It's because we have residual temperature. So this is exactly the mechanism that we are discussing. And the biological example, again, from this paper, measured in the mice neuron, stimulation intensity, which is our case as well, probability varies from 0 to 100%. So we've got a neuron as well. This slide is, well, I decided to include it just yesterday after listening to Xavier's talk, in which he said that coincidence detection is super important in practical applications. So I decided to show that we also have a coincidence detector based on the very same binary 100 nanometer dot. So what is a coincidence detector? It basically fires if A and B, if two pulses arrive within a certain time window, and it doesn't fire if they don't. That's that simple. Causality in this case is not important, so we don't care about which one arrived first. This is what it looks like in biology. So just the fact that you understand from what direction my voice is coming right now is thanks to the coincidence detectors, coincidence detecting neurons in your brain. Because there is an array of coincidence detectors in your brain, you have two ears, and there is a delay. And there are different delays between different coincidence detectors as well. So if this one fires, the brain understands that this delay is the same as this one, and therefore sound is coming from this direction. But in practical applications, it's also very important. I think a Nobel Prize was awarded for the invention of coincidence detector for elementary particles. And our system can do that as well. So we have a region where the probability goes to 1, and we have a region if pulses are too separated, for instance, by 200 nanoseconds, in which the probability is around 0. And we can regulate this by changing the parameters of the spike. If we make them shorter, with larger, smaller amplitude, we can set the shape of this coincidence detection and the region as well. I don't have time to discuss all the properties of this system, so I'll just show you some major things from what I described. We cannot rely right now on CMOS for very large neural networks. What we can rely on is new materials, but synapses and neurons made of these new materials must be uniform in material system, in operating principle, in the spikes that they use. And this is a key requirement, and this, as you could see, follows from the very logic of spiky neural networks. So it's inevitable. And it's hard because synapses and neurons are very different. But it's doable, as we have shown. We did it because of the peculiar switching properties of this material system, and because we could identify the common features between their functionalities. And you can do that as well in your material system if it satisfies these two requirements. So you must be able to tune its switching behavior from binary to memoristive somehow, and you must have a dynamics in the system that you can excite and read out. And antiferromagnets, for instance, just pure antiferromagnets, are almost there because temperature effect is the same, almost the same in them as we have seen in yesterday's talk. And switching behavior is memoristive, but we know that most probably it will become binary if we make the devices small enough. But it doesn't have to be temperature. It can be dynamics of magnetization, for instance, or dynamics of crystallization if you look at a neighboring field. And crystallization dynamics is already used for neurons, but it can be extended perhaps to synapses as well. So it can be any kind of dynamics, in fact, as well as with tunable switching behavior. You don't have to use this exact mechanism. There could be something different. So these are two simple questions that you can use to determine whether your material system is promising for SNNs or not. That's all I have. Thank you.